I just want to position things to introduce OLI, to say that OLI is a global thought leader in electrolyte chemistry. We're proven water chemistry leadership in over 500 companies throughout the world. We have a unique combination of capabilities between physical property modeling and an electrolyte database, and together they produce, or we use them to produce simulation software for water chemistry issues. So we've been in business for 48 years. Our headquarters in New Jersey, USA, but we have uh, colleagues. We have a London subsidiary. We have a Houston office, or we're going to be starting a Houston office. And so there's a lot of expansion going on at OLI. We really are a unique group of professionals who are together to further the electrolyte science. I'm sorry, I still have problems with my mouse and rolling it to advance the screen. Okay, so we use thermodynamics to deliver, to do simulation and to deliver insights, and we do it in 4 different ways. We do it through chemistry analysis, through flow sheet calculations, through corrosion modeling, and through custom applications. And so for each one of these areas, there are programs that work with these areas, and what we're going to be focusing on today is the stream analyzer for chemistry analysis. Why do people use simulation? I like to say that the most important reason is to gain confidence in your recommendations, but what that lets you do is it actually lets you increase your operational efficiency, it lets you reduce risk, and give you a little bit of ability to work faster when you have the backup of thermodynamics with you. I'm sorry. All right. So globally, I think I already mentioned it, we have over 500 successful clients. We span 35 countries and 6 continents. We have the majority of people out of oil and gas or chemicals. We're breaking into the business of metals and mining. We have a following in nuclear, power generation, and water treatment, and in other industries like electronics, for example. So we also work with alliance partners. So we have relationships with AspenTech, with Aviva, with PSE, KBC is a budding one that's going to be happening next year, Honeywell and Syscad, so that when you're using us in the flow sheet environment, you can use us through one of the commercial flow sheet simulators. What we like to say is it's the OLI engine that's delivering simulation power, and it delivers in a wide variety of products, as I showed you, right? So we have 3 different electrolyte frameworks that are available. The MSC framework, which has no concentration limit. It's our newest framework, and it has a lot of our newest chemistry. MSC SRK, which is important if you're doing upstream oil and gas reservoir, especially if you're looking at extreme reservoir conditions, you really want to be in MSC SRK as opposed to MSC, because the SRK is being used for the dense phase and for calculating the hydrocarbons in the second liquid phase. So that's an important thing to remember. And then finally, we have an older framework called the AQ framework, and Diana is going to take you through these frameworks in more depth, just to note that you will be able to really select the framework that makes the most sense for your case on a case-by-case basis. OLI is well published. We're thermodynamicists, so we work with an equation of state and an activity model. We use the Helgerson equation of state. And for an activity model, it is a proprietary model, and it works with the minimization of Gibbs free energy. Andre Andurko is our Chief Technology Officer. He was a postdoc of Professor Pitzer. And so you certainly will see Pitzer influence in our model, but it's not a Pitzer model, it's our own model. We published our models, actually, although I said it was proprietary, we published the equations in peer-reviewed papers. What we consider and what we do hold to ourselves is our databases, which are OLI's competitive edge. There's close to 6,000 species, 81 elements of the periodic table. Let me just, I don't know if you can see that. Can you see that box coming up on my screen? I'm going to just ignore it and hope.
Yes, but it looks just great.
Okay, thank you. So, as I was saying, the databases are our competitive edge with close to 6,000 species, 81 elements of the periodic table. And also we have something interesting, validation spreadsheets, so that when you're trying to gain confidence in your recommendations and you're not really sure whether or not the simulation is accurately modeling what you're doing, you can work with our validation spreadsheets to get more confidence. So as I mentioned before, we bring competitive edge through either chemistry or flow sheeting or corrosion or custom applications. I'm going to just talk a little bit about each one in more depth. So, water chemistry analysis. This is the stream analyzer. We like to say it's a virtual laboratory on your PC. You give it meaning, you get a blank screen or a blank slate of components, and you describe the components and the conditions, and we, in essence, run the experiment for you. Remember that it's equilibrium based. It does distribution between solid, liquid, vapor, and second liquid. It predicts accurately on a multi-component system basis. Now, that's really important to keep in mind. A lot of our problems are going to be with few components so that you can get the calculations very quickly. But keep in mind that you can add any unexpected components, because what the OLI framework does is it takes ternary and binary first and then ternary systems, and it combines them together for what Andre likes to say are reasonable to accurate results when you put everything together in a multi-component system. What that means is very different from a system that has to be interpolated together or regressed together, so that you have some simulators will give you an insert. So here's the way we understand potash chemistry, or here's the way we understand sour water stripping. But if you have, for example, water treatment, and you have an unexpected component that you are dealing with, you don't have to re-regress. You don't have to worry about, is it outside the range of the model, because the model works mostly by adding components. So that's important to know. Lots of advanced mechanisms and advanced properties. I'm going to let the class speak for itself there. In terms of process flow sheet applications, we have really two choices. We either can use an alliance engine when you're working with other thermodynamics, or when there's other features that you need in one of our commercial flow sheet simulators, or you can work in flow sheet ESP when electrolytes are primary. This class is not about flow sheeting, but why do you use flow sheeting? You use it when you have multiple steps in an operation, or multiple units that you want to model, when you have controllers or recycle, and when you have multi-stage capabilities. We have lots of Alliance Engine partners, and we have our own electrolyte system geared for industrial water treatment, where we have things like evaporation, crystallization, and membrane processing that are a little bit tailored for electrolyte processing. I'm going to get this right before too long. Okay, we also have corrosion simulation, which is, we might cover this at the end of the class later on in day 2. If there is interest, we can take a quick look at it. But this class is not going to be about the corrosion analyzer. But keep in mind that we have different ways of predicting corrosion, either general corrosion or localized corrosion. We have stability diagrams, and also an EVS calculation, calculating remaining assets. And if you are interested in that, we can certainly work on that separately, not in this class. Finally, we do custom calculations. This graph is quite interesting. Excuse me? I'm sorry, I thought someone was speaking. Because this little box down here represents OLI today. When I first saw it, I was offended. You know, OLI today actually does a lot. But what this really is trying to say is that you are water chemistry experts, and you are working with the software at this level, but we really can go beyond this level into something that's more automated, where we can do some kind of red, yellow, green flag indication of whether you have a scale that's about to form, or you know, if the scaling tendencies are high. We can move into different levels of cloud performance, and into really our goal with OLI is to get into predictive maintenance facilities, become part of the Internet of Things, and really help clients make digital twins. So this is really OLI's vision for the future, and we are seeking partners. If you are interested in moving past the desktop capability that you have today into some of the areas, automated areas, please let us know, because that's something that we are also interested in doing. Two more things I'd like to say, or maybe a few more slides, but the key to simulation, and what we're going to be doing in this class, is interpreting results. Always, that's the issue. What do I mean by that? Well, process simulation is pretty easy well, not so easy, but you can get some input that you consider representative. You run it through the software, you consider it a black box, you get some output, and then you really need to ask yourself, am I modeling the physical process that I have? If I am, I'm in a really strong position to make recommendations and to come back in and make modifications. So this is really where we want to get, right? But we can't get there except through really the ground of interpretation. So a lot of what you're going to learn today in the class, you're going to learn how to set up the software, how the software works, which features it has. But really, a lot of our focus and why we call it electrolyte modeling basis is so that we can understand how to interpret the results. Because that's really where you're going to get the power of simulation, is when you start to understand, yes, I am modeling my physical process, so I can predict what's going to be happening tomorrow. One of the ways that we have, that we let you do that is we have access to something that we call our validation plots. Now, validation plots are important because what they are showing, this one particularly is showing, it's an arbitrary system of ammonia, sulfuric acid, and water, and it's going across the range of sulfuric acid for a series of isotherms for escalating temperatures between 0 and 100 Celsius. The symbols are experimental data, and the lines are OLI predictions. Now, what is significant about this? First, I didn't mention, but sometimes I do explain that electrolytes are mathematically challenging. And this graph is an example of what's mathematically challenging about electrolytes. You can't really be in this region and predict what's going to happen because there's a whole different behavior. As phase changes, behavior changes. That's a tricky thing about electrolytes, and it's important to know. But the more important thing about this graph is that it's part of our validation plot system. And so if you are a client that's working with us through one of our service levels, you have access to what we call validation discussions. And we can basically show you, oh, are you interested in the system of ammonia, sulfuric acid, and water? Well, here are the references that we've used to regress this data, and here's some of the ways the data looks. So that's an important thing for gaining confidence in the system. If you can see, okay, OLI has actually worked with data sets that cover the span of the range that I'm in, and this looks like a credible result given what I see from the validation plots. So that's how we use them, and it's something to keep in mind. I mentioned service levels. We have service levels that we really recommend. I think if you're in this class and it's complimentary, it's one of the benefits of our service levels. We like to include training, support, consulting, and data validation bundles into them, and that's something that you should just keep in mind. And the final thing I want to say before I turn the class over to Diana is that we do a lot on LinkedIn in our OLI simulation group. And so I think that you'll be all encouraged to follow OLI systems and to join our simulation group, where you have easy access to all of the OLI team, keeps track on social media. So that's something that you should be aware of. It's a good time to ask questions if anybody has any questions. And if not, I'm going to turn it over to Diana.
So these are the main course objectives for the class. So, but I think that the most important objective for me is that, again, at the end of this course, you will be able to formulate and interpret the results of your simulation to optimize your process or applications, and also that you just use the software as a quick tool to simulate calculations that you want to do instead of spending, like it was mentioned before, rather than doing a manual calculation. The software can just save you a lot of time, and that you are able to formulate and build these cases really quickly in the software. So this training will be divided into 2 days. Each session will be 3 hours, and then we will be working around 53 minutes to 55 minutes, and then we will take a quick break of 5 to 7 minutes. And I just want to mention, if somebody is working with one screen, you can always split your screen so that you can see the presentation and how I am working in the software. And then you can also work with your software at the same time. So to do that, use the Windows key, and then you can use the left or the right key in your keyboard to split your screen if you need to do so. So the materials for this class are the software. So you should have received a serial number that is giving you access to both Stream Analyzer and the Corrosion Analyzer. So just make sure that you had these two. We will make sure in a moment if we are having this the corrosion analyzer, because we will be working a little bit with corrosion rates and pore bait diagrams, and in the second day. So if you have any questions about installation or if you're having issues, please let me know before we start so that we can fix that issue. And also, you should have, during this training, you should also have received a manual. And during this training, I will walk through the essence of the manual, and I will also provide the files that we create during this course so that you have them for future reference. This is the course agenda. So today, we are going to introduce the Stream Analyzer tool. We will learn about the user interface, how to do a stream definition, and then we are going to cover the types of calculations that we have in the software, and then we will learn how to analyze the results in the tables and in the plots, and how to export this data for your reference in the future. Also, in the second day, we are going to learn how to do water analysis, mixers, and I will give a brief introduction of the OLI Studio Corrosion Analyzer. During this course, please let me know if you have any technical issues, and also if you need to leave for a moment, just let me know. And please mute your devices so that we don't have interruption during the course. You can put them either in mute or silence, so that, yeah, they don't give interruptions today. And please actively participate and feel free to interrupt if you have any questions. So if you have questions, you can just raise your hand next to your participant name. You will see a little hand, and then you can just raise, and I will be able to see if you have questions. You can also use the chat to ask any questions if you have here, or just, if you are muted, just unmute yourself and ask the question. Don't hesitate. At the end of this course, you will receive a certificate of completion, and also will be receiving a link for a survey to rate this course. So thank you in advance for filling out that survey. And after this course, you can always contact OLI support via web, email, or phone. And if you have any technical issues, you can contact us. If you have technical questions, we will be happy to help. So this is our information. So now onto the class. The first tool that we are going to analyze is the OLI Studio Stream Analyzer. And this Stream Analyzer is the main interface of OLI Studio. And in a nutshell, what does OLI Studio Stream Analyzer do? Well, Stream Analyzer calculates electrolyte solution properties based on electrolyte models that have been validated with experimental data, and uses these properties to drive simulations. There are three models. We have the AQ model, the mixed solvent electrolyte model, or MSE, and the mixed solvent electrolyte and Schwabi-Redlich-Kwong model, the MSE-SRK model, that you have them available in the Stream Analyzer. Okay. Now you can see the OLI software as a chemistry lab in your computer, and this chemistry lab will allow you to analyze molecular inflows, which are typical of a processed stream, and ionic inflows, typical of a sample of water analysis. And we will cover this in detail. So the first thing that we are going to learn this morning, or depending upon you are located this afternoon, is the user interface. So in the OLI Studio software, we have the OLI Studio desktop user interface, which provides the environment to create, analyze, and interpret the results of your application chemistry. I will give you an overview of the different windows and tools that you will be able to use within the software, as well as how to navigate the OLI Studio user interface. So when you open the software for the first time, this is the window that you will see. And you can see that there are different parts of the user interface. We have the toolbar, the navigator pane, the actions pane, plot template manager, and I will describe this in a little bit more detail. So please go ahead and open the software. So if you have installed the software, you should be able to see the icon of OLI Studio 9.6. And just click on the icon. And this will bring this screen, which will be the OLI Studio interface. And I will maximize this window just to make sure that everybody can see it. Does everybody have the software open at the moment? Is it?
Yes. Yes.
Okay, good. That's good. Okay, so let me just quickly go back to the presentation here. And okay, so I will start with describing the navigator panel. Okay, so in this navigator panel, you can open or add additional files. This makes it possible to access different documents very easily. So in here you create a new document, or you can always go and open a previous document that you have worked on before. Let's say you open this new document in here. So you can always access very easily several documents using the navigator panel, as you can see. So you can open several documents in this navigator panel. Now, in this navigator panel also contains the list of streams and the different calculations that are active within the file. So you will find 4 different levels of calculation. The first level is the global stream level. And in here, when you click here, you will be able to set up units, the name style of your components, and the general preferred options. The next level is the stream level, which is this one, which is identified by this drop of water icon. It looks like a drop of water. And then within the stream, we also have a sub-calculate, or we have what we call the calculation level. This could be what we call, could be a single point calculation, like this one, or it could be a survey calculation. And again, I will describe this in more detail, the types of calculation. And finally, within the survey calculation, then you can see the sub-calculation level. And if you click on this plus sign here, you will be able to see all of the results for each point of the survey. So those are the 4 levels that you will see in the navigator panel. Another feature of the navigator panel is that you can track calculations from one document to another. So let's say I want this survey calculation, and I want to take it to my new document, the document 1, and I can drag it in this white region in my document 1. So then I can start a new calculation. So that's the advantage of having the ability to open different documents in the navigator panel. Okay, so that is the navigator panel. Now, next, we have this actions panel. And in the actions panel, you can see all of the objects that are installed in the software. If we go to the stream level, we can see all of the objects. If we go to the stream level, you can see the calculations that you can do within a stream. So let's go to the stream, the global stream, and this will be all the objects that, if you have all of the add-ons, like scale chem, corrosion analyzer, and stream analyzer, those will be the objects that you will see installed in the software. Now, each icon in here represents either a new stream or a new type of calculation. Okay. Now, you probably at this moment you may have different options, a different view here for the actions panel. You may see the icons. Probably you are seeing this view. I personally prefer the view list. So what I do is right-click on that white area, and I click on the list view, just because it just makes it easier to see all of the actions or the icons in this actions panel. Now, the next part of the software, or the next toolbar, is this quick access toolbar that we see up here. So what this toolbar will allow us is to give us quick access to different functions. The most used one is the save button, of course. Every time that we are doing a calculation, we just want to save quickly our file. But if you see these icons in here are grayed out, and the reason why is because we are at the stream level, at the global stream level. So this will be enabled when we click on the stream level, where we see the water icon stream. And then you will see that now you have all of these options enabled. So the bar that we'll use the most is this bar that we call the chemistry bar, and also this little bar here that we call the quick access tool bar. This will be the ones that we use the most. In the chemistry bar, you will have access to, for example, you can turn on or turn off different phases for your calculations. The L1 stands for the aqueous phase or liquid one. VA stands for vapor phase, SO for solid phase, and L2 for the organic phase. This RE button here, it stands for enabling redox reactions. And then we have here these three buttons that will allow us to select the thermodynamic framework, the AQ, MSc SRK, and MSc. So whenever you turn on any of these options, if you click, for example, on the redox button, you will see that it will be highlighted in blue, in light blue, and when it's off, it will go back to a gray color. Okay, now in this quick tools bar, we can see different options, and the most used ones is this component search that looks like little binoculars. So if you open or click on it, it will open this component search window. And whenever you are working, for example, we have selected here the MSc data bank. So it's going to search a component within this data bank. So you want to know if the MSc has benzene, for example. So you can type benzene, and it finds the component in the software, and it will let you know the molecular weight, the CAS number, the formula name, etc. So you can always make sure if a component is in our database using this component search option. The next tool that we will use a lot is this names manager. It looks with an NaCl. Do we have a question? Is here? Okay, so we have the names manager. This names manager allows us to change the way the component names will appear on tables and reports. So we have three different types of style options. We have the name, the formula name or the OLI name. And finally, the one that we will use the most is this units manager. And what it will allow you is to change to preferred units for your calculations. You can just click here in the customize button, and then you can change if you want units in volume, concentration, mass fraction. You can always edit this just by accessing the units manager button here. Okay, so that is the bar that we have, the quick access bar up here. Now you also see this plot template manager to the left. That is an option where when we are having a lot of or plotting a lot of different results, in here you can save and have access to the commonly used plots, and I will show this later also in the course how to use it. And down here you see the calculation output panel, and whenever you are running a calculation, for example here I'll run this survey. This calculation output, in here you will receive warnings or calculation failures, or if the calculation is complete. So it will let you know, like in case you have a, like your case didn't converge or didn't run for some reason. In here you can always read and understand the cause of error. Okay, so there is another panel here that is not shown by default, but in so many cases it's very useful to have, and that is the object library. That object library is very important, especially when we are doing water analysis, because we have to enter so many ions and cations, and we don't want to do it all over again from the beginning. So that will be the object library, and you can bring that object library if you go to the view and then go to toolbars and then select object library. So again, this object library in here appears to the right of your screen, and you will see commonly used objects in here. You can see that we have standard seawater analysis, we have dry air, pseudo components, another type of water analysis, etc. So what you can do is, let's say you want to do water analysis or standard seawater analysis, you click on it, and the next thing that you can do is just drag it to the navigator panel, and then you will see that this seawater analysis now appears here and is already pre-populated with this data. This standard seawater analysis, I believe it comes from ASTM standard. So every time that you want to know, if you're running an experiment and you want to know the pH or specific electrical conductivity, you can just bring it really quickly and analyze those results. Another thing is, these are the standard objects that the software has, but you can also create your own objects. So let's say you created this water analysis, a new water analysis with your own data. Here will be 500. You have measured pH of 8.5, etc. So once you have, and you know that you will be using this water analysis for future, you can also just drag this object and put it into your own objects for future reference, and you will have it there. We will be using this object library when we go through the water analysis section of this course. Also, you can just get, we're not going to use it here, I just want to make sure that we know how to bring this object library. So I'm going to close it, and let's say that also by default or by accident, I just click on this X, in this little X here for the navigator panel, and I no longer see my navigator panel. So what you can do is just go to View, Toolbars, and make sure to click on the navigator option, and the navigator panel will appear again. So if just by accident you miss or lose any of these windows, you can always go to view toolbars and select the ones that you are missing. Just that's a quick tip, because sometimes it has happened to me that I just click by accident on those little X's, and then I'm confused, like why is it not there? So it's an easy fix. And finally, I would like to show you the workspace. The workspace is where we are going to spend most of our time entering data, where we are going to analyze our chemistry, and when we are going to analyze our results. And depending on the object that you select, different tabs will be shown in this workspace option. So in this case, I have selected a survey calculation down here. So you can see that, for example, for this survey calculation, you have the description panel or the description tab, and in here you can read or add a description of the selected calculation. So you can add your name, and in here you can say, okay, in here we are analyzing the solubility of sodium chloride as a function of temperature. So this is important because sometimes we run so many calculations and then we forget what were the specifics of the calculation. So this description panel allow us to put descriptions about that specific calculation. Then we have the definition tab, and in here is where we are going to enter the stream composition and also the specifics. So let me just change this to just add also a single point here. So in this single point, you will see that you will enter the stream parameters. You'll see that you have the stream amount, temperature, and pressure. And in here, basically, you will define all your chemistry. Then we have the plot tab. And in here, you can view the results in a plot format, or you can also view your results in a table format. So you always have the option to see the results in either in plot or in the table in tabular form. And finally, you will see this report tab. And in here, you will see different tables with all the inputs and results of your simulation. And we will go through this report tab in more detail later. And also in the workspace, you will find the summary section, this small white area to the right. And in this summary section, you will have a quick summary of the stream definition and also some quick summary of the results of your simulation. So this is only for the survey calculation, but you will see that whenever we are doing corrosion rate or a pore rate diagram or water analysis, these tabs are here, up here will change, but as we go in the course, I will introduce and explain each one of these tabs for each calculation type. In most of the time, our workspace it will look very familiar most of the time, but I will make sure to introduce new parts that we see as we go in the course. Okay, so this is what I already talked about, the toolbar, the names manager. You will have these slides for future reference too, so that you have a little bit of, you remember where to find all of these specific options. This is the object library, the workspace. And now I would like to make a last comment before we start working in the software. There are 3 different thermodynamic frameworks in OLI. In here I have put just general rules to get an idea when to use which framework. So whenever we are using, or we have the stream that we have is 70% aqueous phase. If this stream is 70% water phase, we can use the AQ framework. As long as it's a solution that has a lot of water, we are good with the AQ framework. If the water content is less than 70% of the stream, then it would be a good idea to use the MSC framework. And this is a preferred data bank when we have very saturated solutions. So if we have a very concentrated salt solution, the MSC is the framework to select. And finally, we have the MSC SRK. This MSC SRK was developed specifically for upstream oil and gas applications that contain light hydrocarbons like methane and also CO2 and H2S, and when we require high pressures above 80 atmospheres. So this framework will be only for upstream oil and gas applications, and when we are dealing with normal temperatures and pressures, then we can either go with the AQ or MSC. Currently, OLI is developing a feature that will help the customer to select the best framework for his or her application. So it's coming up in a future release, but at the moment this is just a general rule that I personally use when I'm doing simulations. Okay, so this ends the presentation part about the user interface in OLI Studio. We will have more time to go through it, and we will, with the examples, we will get more familiar with it. And now we can start doing work in the software. But, okay, so it's 9:53 a.m. Pat, do you think we should get a break before we...
I would actually see if we can go a little bit longer to do the first calculation and then break, because we're waiting to get into the software. And it won't take you that long.
Okay. Okay, so I will quickly introduce the calculation types. When we are in Stream Analyzer, for all calculations, we will create one or more objects, and it's referred to as streams, and that will be this button that you see here to the right. And in here you will define temperature, chemistry, pressure, and all of the conditions that you know for this stream. And for the Stream Analyzer, you have 5 different calculations. You have the single point calculation, the survey calculation, and then the mixer calculation and the chemical diagram. This add water analysis is another way to create a stream, but in an ionic form, and then we will be able to do what we call a reconciliation calculation. And for the corrosion analyzer tool, then we have the add stability diagram option and the corrosion rates. So we will start with single point calculations. And single point calculations are used to find information at one specific equilibrium state. These are the simplest set of calculations in the software, and we have 13 of them. And we will cover the majority of them. I'll cover isothermal, bubble point, dew point, vapor fraction, precipitation point, set pH. And in here you will see just, this is for your reference, this is when if you want to remember what an isothermal calculation is, a bubble point, composition point, etc. So this is, again, you will have it here for future reference. So, okay, so let's go into our first example. We will calculate the properties of a 1 molal NaCl solution. So I will show you how to set up this isothermal calculation, and then we will explore where to find the results of the simulation. So let's start with a new document. Oh, I will start with a new document here in the software. So let's bring the software. Oops, what happened here? I'll just start a new document. And the first step is to add a stream. So we click on this, see my actions panel went away. When we click here in the global stream, so we will be able to see the add stream icon. You can add a stream either by double clicking this add stream, or you can also go to the streams, add stream, and it will add a new stream. Okay, I don't want this extra stream, so I will right click and delete it. And once we have created this stream, we can change the name to isothermal calculations. So to do that, you can either select it and then hit the F2 key, and it will allow you to change the name. You also have the option to double click on it and change the name. Right click is the other option, and then rename. Or you can go to the description tab, and then we can change the name here to isothermal calculations. And then if you want to add a description here, we can say setting up an isothermal calculation. Okay. Then the next step is to go to the definition tab. And again, in here we are going to define our stream. The stream amount means the size of the stream. By default is 55.5082 moles. This is the same as 1 kilogram of water. The software puts it in moles because it's once you put the moles here, for example, of our stream under the inflows, you put here NaCl, and if you enter 1 mole, if you write and then click enter, and then it will take you to the next cell in here, and then we can enter the number 1. So the reason why we have water as 55.5082 is because when we enter this 1 mole of sodium chloride, this will create a 1 molal solution of sodium chloride, because this is 1 mole over 1 kilogram of water. Then we can define our temperature. I will leave it as 25 degrees C, and then the pressure 1 atmosphere. And notice that the moles, of course, is the default unit. For this calculation, I want to select the AQ framework because it's just a dilute solution, so I'm going to use the AQ framework. And then I want you to notice also something in this calculation, and is that there are 3 different colors. There is a color-coded cell. These cells are color-coded. So whenever you see these yellow cells, it means that these cells are not editable. You cannot change, you cannot overwrite these numbers. Whatever is in the white color, so is where you can enter new information. And whenever you see this green cell, is because the software will calculate automatically that stream. Okay. So now we have already created our chemistry here. The next step is to add a calculation type. So if you go to the right, you see the Add Calculation button. Just click on it, and you can select Single Point Calculation. You can also select the Single Point Calculation in the Actions panel by double-clicking, and then it will create a single point calculation under the stream. You can name this as a 1 molal, double click on it, and change the name to 1 molal NaCl. Okay, and notice that now, because we put that type of calculation, we have this button that says calculate and it's green, indicating that we have defined all of the inputs necessary to calculate this stream or this specific single point. So another, well, I'll show that in a moment, but let's click calculate. And to the right in the summary, you can see a summary of the results. In here, you can see that the pH of the solution is around 6.98. It has calculated the ionic strength, density, etc. This is one quick way of seeing the results. The other way to analyze the results is to go to this output tab here. So if you click on it, you will see that all of this is highlighted in yellow, meaning that it was used for the calculation and you cannot use it. Now, you want to see some results, so you will need to right-click on the gray area and then go to sections. And you will see lots of categories in here where you will be able to select, for example, in this case, I want to see additional stream parameters. I click on it, and it will bring this grid with my results. It will be the density, ionic strength, and pH. Okay. There is another section that I would like to see, and that would be the aqueous phase or the aqueous species. And in here, it will give you the speciation that is happening for this calculation of 1 molal NaCl. And the third way of analyzing results is the report tab. So in here, you will see different tables. If you click in this jump to.
Diana, this is probably where we should break because there's so much information in this report, yeah?
Okay, yeah, we can go to, we can take a break and then I'll explain this really quickly and then we'll move to another calculation. Okay, so let's stop here for the moment, and then we will go back here for the reports, and then we'll continue with another calculation. Okay, so we'll be here, let's take around 5 minutes, and we'll be back at 10:08 or 10:09 a.m. Let's say 10:10, so we can continue with the session. Thank you. Okay, so it looks like it's around 10:09. Okay, so is everybody back from the quick break?
That's always a crazy question because if people aren't here, they can't answer.
Yeah, so how should I ask the question?
Please not back. Raise your hand.
Please say, I am here.
Yeah,
So,
if you could tell us you're back.
yeah, please tell us if you are back.
JC here.
Okay, great. Who else here?
Agentia here.
Good.
Samira's here.
Okay, good. So we're missing.
Yan and Rosman.
Yeah. We didn't get the introduction of.
I'm back. Ian.
Great.
Okay, so it looks like everybody's back. That's good. So we were here at the 1-molal NaCl calculations. Does somebody have a question regarding how to set up this calculation? I was going to go through the report saying that you will find different types of information here, but I will go in more detail later in the course when we are doing, for example, scaling tendencies, and we can analyze this data. But are there any questions about the functionalities, the solid, in here, the chemistry tab, how to change units, or how to set up the calculation? Okay. So the next calculation that we are going to do, and I would like that everybody just follows with this calculation, is the isothermal calculation for 1-molal iron chloride. Okay, so we are going to add a single point calculation, and we are going to name it 1-molal iron chloride. And before we do the isothermal calculation, could somebody have an idea or give me an idea of the pH of this solution? What do you think would be the pH of a 1-molal iron chloride in water? Somebody wants to guess? The previous calculation, we had a pH almost 7. What would be the pH? An idea for this new pH?
We'll go with 6.
You would say 6. JC says
1.
1. Oh, wow. Okay. And Jan says 6. Okay. So let's set up this. So if we click on the isothermal calculation, then we can add a single point, either here again or add calculation, and let's set this calculation point. Let's name it, double click on it, and 1-molal iron chloride. And I want you to notice something, and is that when we set up this isothermal calculation, we put this NaCl, and the NaCl and the 1-molal was editable. It's in the white cell, so you can edit this. But once you add a new calculation, a sub-calculation level or a calculation level here, then the NaCl is in yellow. You cannot change this. However, you can continue adding more chemistry here. So if we are going to do the 1-molal iron chloride, we will see that the NaCl cannot be moved, cannot be removed because it's fixed. So we are going to put 0 for the NaCl, and we are going to add in the white cell FeCl3, and then we are going to add 1-molal. For this calculation, AQ model is a very diluted solution, so we are going to calculate.
Sorry, I missed. How do you add another calculation?
Oh, okay, yes, sure. So you go to you click on the stream that is named isothermal calculation.
Okay.
Okay. And it will give you these different actions. And then you
add a single point. Okay.
Add single point.
All right.
Or you have the option to the right, add calculation, single point.
Okay, thank you.
No. Okay, so the results, the quick summary results here. And then you can see that this pH is calculated around 2.2. So JC, you were almost there. The pH, why do you think the pH was so low? You did a very good guess for the pH. So why do you think this pH was very low for this specific solution?
That's a good question. I'm not 100% sure.
Is that
I was kind of basing it on 6 based on adding ferric chloride to waters in the past, but.
Yeah. Okay. Yeah. So I will quickly explain what's going on here. So yeah, definitely the pH is very low. This is one of these salts that when they react with water and we have these hydrolysis reactions, they are going to asphyxiate and they are going to form this F3+ in solution. And this F3+ in solution then reacts with water and it starts to release H+ in our system. And this H+ is what, as it increases, as we dissociate this iron chloride in solution, then we have more and more, and according to the pH calculation here, if we have more hydrogen in our water, our pH is going to be very low because we have this minus log of the concentration and the activity coefficient. Now, the software is not only calculating this concentration of hydrogen plus in solution, it's also calculating this activity coefficient, and that is how the software is calculating this pH. Okay, so let me just go back to the software. We can go to the report, and in the report we can, well, let's go to the output tab here. And if we right click on this output tab and then go to sections, then go to the aqueous section here, you will see all of the different speciations that the iron 3+ cause here. So once you react with water, you start seeing the formation of all of these different species in solution, and you can see the concentration of H+. And if you want to be a little bit, okay, I'm curious about the activity coefficients. I know that maybe that's too much, but I will show them really quickly. You can also see the activity coefficients for those specific species. If you use this H+, activity coefficient, and the concentration, you will calculate a pH of 2.21. Okay, so that is the isothermal calculation. Is there any question of how to set up this calculation that you would like to know more about? Or is any other calculation or chemical that you want to use?
Sorry, my situation may be specific to myself. I did get the right 2-point-something pH, but when I click the displaying the aqueous component, everything is 0.
Which the aqueous component here, the H+ is 0?
Yeah, everything is 0.
Everything is 0, and you are in the AQ model.
Yes.
So you can ask to share your screen, yeah? We can see the screen, and then we can probably quickly diagnose it.
Yes, we can do that. Yes, definitely. So if you go in the
You need to make
first
presenter.
part. Yeah. How can?
I usually do it on the participant list on the right.
Okay, so this was Yang. Sure. Okay, now you're the presenter.
Right. And now just share your screen, go up to share,
Okay.
and share content. You share monitor. Yeah, good. And then move it over so that we can, all right, and then we can see what
And
happens.
we'll go to the output. Okay.
So I add the section aqueous.
Oh, I see. Okay, so what you need to do is go, you see in the left corner, there is the output tab, down the left corner, down the software.
Down.
It says advanced search, add as a string.
Okay.
So you go to output, right click on the gray area, sections, aqueous.
Aqueous.
Down a little bit lower, there.
Past it.
You passed it. There it is, yeah.
Okay.
Then
Thank
you will see the concentrations or the species, the concentration of each one of the species. So that's good.
Okay.
Okay, so yeah, when we are looking at results, we always need to go to the output tab, or we can always go to the report tab. So it's okay. You have several options to show the results. So, for example, in there, if you want to see the species, so what you need to do is, scroll down and you will see the species right there, and which the concentration.
So Diana, if you want to see these species in percentages, is that possible as opposed to
Yes,
whole?
yes, definitely. If you, Jan, could you please scroll down really quickly? I just want to see one thing. You can also analyze, you see the element distribution. Well, this will be specifically for element distribution. But what you can do is always change the units. And you can, instead of saying show me moles, you can always show the mass percent, mass fraction, mole fraction, etc. So you will be able to see when you select that. And there will be tables where you will see how much of that, the percentage of the total is each one of the species. Let me see if I can just, okay, I'm going to take control back, and then I will share my screen.
Yeah.
Share content. Okay. This is my screen. So let me see. I have seen that, so let me see if I change the units manager to mass fraction. So let's apply this. Let me see one thing. Okay. So if we go to the report, here will tell you the in moles, kilograms, and liters, and you will see the mass fractions. Is this what you were asking for, JC? Or this will just change to mass fraction, the units. It will represent, and in here it will tell you the element distribution, the oxidation state of every single element and how it's distributed in the aqueous phase.
Yeah, I think so, but we've lost your screen.
Yeah.
Oh, you're not watching my screen?
No.
No, it's gone.
Because we have, instead, Diana, we have all of the people's names. So maybe that's the other terminal. Oh,
Okay.
He's still the presenter. You didn't take presenter back.
Oh. No one. Okay.
Here we go.
And I was talking here like, oh, click here. Okay, so when you go to the units manager, then you can always change the metric, batch, and mass fraction units. And this will change all your units. Then you go to the report, and in here, you will see all the species as a mass fraction, mass percent. And you will also be able to see the element distribution, the oxidation state of every single element, and the total percentage of.
That's perfect. Thank you.
This is what you were asking?
Yeah, absolutely. That's
Okay,
excellent.
that's great.
Thank you.
Okay. Okay, so it's important that we get very familiar with the isothermal calculation, because once we get comfortable with the isothermal calculation, then we can move to more specific, other specific calculations. So this is the isothermal calculation, okay? So now we are going to transition to the phase equilibria calculations. So in this the next examples I'm going to cover are the bubble point, dew point, precipitation point, and the vapor fraction. The bubble point is whenever you want to know, okay, what is the concentration effect on the boiling point or in the dew point. So you can study that. The precipitation point is where you want to understand the solubility of a specific salt in water. And the vapor fraction, I find it very, very important, because sometimes you want to do an evaporation step and you want to analyze what solids precipitated out. So those four are the next calculations we are going to cover. So the example number 3 for today is bubble point. So we will start, in this example, we are going to compute the bubble point temperature of a 6 mass% acetone solution at a constant pressure. Okay, so this will be under isobaric conditions. And then we'll change the calculation to change the bubble point pressure at a constant temperature. Okay, so let's go back to the software. And the next step, or the first step that we need to do, is to add a stream. So double click on add stream on the add stream icon. So we have a new stream. Okay. So let's rename it bubble point. And for this example, let's use the MSC framework. So click on the MSC framework. Okay. And now let's enter acetone in the inflows. So let's just type acetone. Now I want you to notice something here. The software immediately changed the name to the formula name. Okay, so if you mouse over the name, you will see the different names, the acetone formula name, the OLI name. And if you don't like how the software is presenting these names, so you can always go to the names manager and just say, okay, display my name, because I feel more comfortable reading acetone than CH3, etc. So let's leave that default name for this example. And since we are going to do a bubble point calculation for a 6 mass% acetone solution, we need to change the units. And the next step is to click on the units manager. And then this will bring the units manager for the bubble point. So again, we are doing the stream calculation, bubble point. This will change the units for the bubble point calculation. So then click metric. So we are going to select metric batch. And for this specific calculation, let's select mass fraction. Okay. Then click OK. And notice how my units have changed here to mass fraction. And my stream amount now is no longer moles, it's 1 kilogram. Changed from moles to 1 kilogram. Okay, so now that we have entered this chemistry, we need to add the calculation. So go to the right, add calculation button, and then click on single point calculation. Okay. The type of calculation by default is the isothermal calculation, and what I want to calculate is the bubble point calculation. So let's change this, click on isothermal, and it will bring the different options. So let's click on bubble point calculation. Okay, so let's change this single point name to bubble point temperature, PPT. And notice that in this grid, now we have an extra section called calculation parameters. And this calculation parameters is saying, okay, you want to calculate the bubble point, but what do you want, temperature or pressure? So in this case, I want to calculate the bubble point temperature. And so you notice that now my temperature is it has a green color. The 25 number has a green color, and it means that that is the initial value that the software is going to use, and the pressure is fixed. The pressure is going to be fixed, okay, at 1 atmosphere. Okay, so this yellow button here means, okay, I will vary or I will free this variable temperature, and this brown button here means, okay, this variable is fixed, this pressure is fixed. So calculate bubble point temperature, so we are ready, and then click calculate. Another way to calculate that I have forgotten to mention is that you can just simply press the F9 key, and it will also calculate instead of clicking on the calculate button. So for this specific calculation, you see here, the pH is around 6.12 of the solution. And if we want to see more, we want to know what is the bubble point calculation of this acetone. Oh, wow, sorry, I did not enter the mass percentage here of acetone. So please go back to the stream, bubble point, acetone, and we need to enter the concentration of that acetone. So let's just enter 6, the number 6, and that will change the total mass, the mass percentage of water. Water will be now 94%, and acetone will be 6. Sorry about that, I forgot about that number. And then go back to the single point calculation, and then click calculate. And this calculation is telling me that the bubble point temperature is around 87.25 degrees C at 1 atmosphere, and that my pH is 6.23. Now, if we go to the report, one of the tables that the one that I want to analyze for this specific calculation is called the total and phase flow amount. So if you click here in the jump to, select the total and phase flows amounts, and it will bring you to this table. And notice that the vapor amount that was calculated for this calculation is very small. It's 5.3 times to the minus 9 moles. And you can see that this small vapor amount is basically 1 times 10 to the minus 10, the total stream. So what the software is doing is that it's saying, okay, we are going to form a very small amount of vapor, very small. That will be our first bubble that is going to be formed. And the software has fixed the amount of vapor to be 1 times 10 to the minus 10 of the total stream. And here you can see that that is the case. You can also see the results in kilograms, liters, but within the code in the software is always the amount of moles. That is the value that is selected for this specific calculation. Okay. Any questions about the bubble point calculation?
What does the bubble point actually mean?
Okay, it's basically the
boiling point?
It's basically the boiling point. So if you have a specific solution of salt, let's say sodium chloride and water, you want to know exactly at what temperature it starts to boil, and it forms the first bubble. So when you have the formation of the first bubble, that means that the solution has reached its boiling point.
Perfect, thank you.
Yes. So you can also do bubble point pressure, and that would be, it will stay at a constant temperature, and then it will calculate the pressure at which you form the first bubble. And to do that, just let's do it really quickly. You can copy this calculation, the bubble point temperature, and paste it on the bubble point stream. Paste. And let's change the name. Bubble point pressure, BPP. And in the calculate grid, just change the temperature to pressure. And then you click calculate. And it will tell you, okay, at 25 degrees C, your water, this solution will start boiling at 0.07 atmospheres. Okay? Okay, so this is the bubble point. Now, the next calculation I want to introduce is called the dew point. So for the dew point is defined as the temperature or pressure at which a condensable component of a gas starts to condensate into liquid. So the example that I have for today is that, for example, you have air, and you know air has all of these gases, and there is a little bit of water in the air. That will be the humidity of the air. So we are going to calculate at which temperature the water that is present in air starts to condensate. Okay, so that will be the next calculation. I know that the dew point is also very, very useful when there are corrosion studies. So people want to understand what is the composition of a specific dew point, or the first drop of water that is formed, because once they know that specific concentration, they can predict the corrosion that can happen on a pipeline. That's another application of the dew point. So for the dew point, let's add a new stream, and let's name it dew point. I will use the AQ framework for that. And for the names, not only we have the name, I want to go back to the formula, and let's enter the following components. So we have water. I want to enter, yes?
Diana, I want to ask a question. So if we're modeling gas, wouldn't we want to choose the MSE framework? Or is it because...
Yes, we could also, yes, the MSE one for gas. Yes, yes. Actually, the MSE framework would be a best one to use for this specific example. Because we have water, yes. We don't have very much amount of water in the stream. So yeah, let's change it to the MSE. Yeah, thank you for that. Yes, you're right. MSE would work for this case better. So for water, let's add 2.5. Now, nitrogen, I'm going to enter the composition of air now. So 76 moles. Oxygen, 21 moles. Argon, that would be 0.6. And CO2, that would be 0.04. This is then, I'm pretty sure I didn't enter something weird here. Okay. So we have the MSC. We enter the composition of my gas in my inflows, and now we're ready to add a calculation. So this will be the single point. And then instead of isothermal, then I want a dew point. And by default, the software says, okay, we can calculate the dew point temperature. You, in this case, also have the option of the dew point pressure. Okay? So let's do temperature for this example. And let's calculate. Okay, so to the right, again, the software is telling me that at 1 atmosphere, the water that is present in my air will start condensating at 21.2 degrees C. Okay, and now for the phase amounts, again, you can see that we have a total amount of 114 moles, and the aqueous phase, which is the first drop of water that we are having, that is forming, is 1 times 10 to the minus 6 times the total stream. We can also see that again in the report. It's more clear if we go to the total phase flows. So in here, you can see that my liquid one, or the aqueous phase, is 10 times 10 to the minus 6, the total amount of my stream. So that's the value the software has picked by default. Okay? And again, you can also copy and paste. Oh, let's name it this. This is the dew point temperature. So if you want to calculate the dew point pressure, you can copy and paste on dew point. Change the name to dew point pressure, DPP. Change the calculate pressure, and then it will calculate the pressure at which it will form the first drop of water. It will be 125.8 atmospheres. Okay. This is how we set up a dew point. It's very simple. Any questions about dew point? I know this is very useful for corrosion applications, this specific one. I happen to do one with air, but maybe next time I will present one with H2S concentration in the vapor phase and analyze that. Okay. Our last, no, this is not the last. This is the next one is the precipitation point. This is our third type of calculation I want to introduce. This would be the precipitation point. So the precipitation point calculation will help you calculate the amount of, the precipitation point calculation will compute the amount of material that is held in solution at given conditions and forces a very small amount of solid to precipitate. So you can also see this calculation as the solubility calculation. Okay. So what we are going to do here is we will compute the solubility of a calcium carbonate as calcite in water. So let's go back to the software. Let's add a new stream. And we are going to rename it precipitation point. Good. For this precipitation point, we can use the AQ framework. And when we are working with solubilities, the preferred units are the milligrams per liter. So to do that, we can change the units in the units manager. And then let's change from moles to concentration in this case. And then click OK. So that concentration will be given in milligrams per liter. And immediately you can see here that my units change. And we have a total stream amount of 1 liter. So also the stream amount units change to 1 liter. Okay. So for this calculation, we want to understand or calculate the solubility of calcium carbonate. So let's enter calcium carbonate. Enter. And because the software will be calculating how much of this calcium carbonate is added, I won't put any concentration of calcium carbonate at the moment. So the next step is go to the Add Calculation button and click on the single point and change it to precipitation point. And this new precipitation point, let's call it calcite solubility. Okay. So notice that now we have a new grid here. We have the calculation parameters grid where the software is asking, okay, what do you want to precipitate and what do you want to adjust? So, okay, we say we need to precipitate calcium carbonate as calcite. So we need to select it here. Also, you can see here that there is a warning message saying, please select the target solid and select the variable to adjust. It's telling you, okay, please select here what you want to precipitate. So select calcium carbonate, calcite, and the adjusted inflow would be, please change this amount of calcium carbonate in my inflows. And then we are ready to calculate. You can also go to the specs button and it will ask you the same question here. It will say, okay, what is your precipitant and what is the value that you want to adjust? And we already told it calcite for the solid and the variable I want to adjust, calcium carbonate. Okay, so let's calculate this. And okay, so in here to the right again, the software said in order to precipitate a small amount of calcium carbonate as calcite, the software needed to add 12.13 milligrams per liter of calcite. So let's go to the report. I always like to go to the report because you can see more information there. So in this report, actually, there is not like how much the software added to the stream as calcium carbonate. So what we need to do is go to the Customize button here. And in here, these are all of the other reports that you can show in there. So the one that I want to select here is the stream inflows. So let's select this stream inflows and then click OK. So again, in here is in the stream inflows, it says, okay, in my output, what the software had to add was 12.34 milligrams per liter of calcium carbonate to precipitate a small amount of calcite. And down here, you can see in the total and phase flows, you can see that the solid is also a very small amount, and it's set as 1 times 10 to the minus 8 of the total stream amount. It's always going to be a very small amount for the software in order to calculate this precipitation point or the dew point or the bubble point. Okay, any questions about this precipitation point calculation? You can also find here the pH is a very high pH calcium carbonate solution. Okay. So I will assume this precipitation point is clear. And then now we are going to move to our last calculation for the phase equilibrium, and that would be the vapor fraction. So the vapor fraction calculation allows us to set a specific fraction of the total stream in the vapor phase. So this type of calculation can be seen as a evaporation step. And this calculation is very identical in nature to the bubble point calculation, except that instead of the software defining the vapor amount as 1 times 10 to the minus 10 of the total stream, the user defines the vapor size in either mole fraction units, that will be the vapor fraction, or mole units, that will be the vapor amount. So to illustrate this type of calculation, we will evaporate a brine to study its final composition. So let's go back to the software and let's add a new stream. And we are going to name this new stream as evaporation. Okay. we're going to select we can select here the AQ framework, and I want to change these inflows units to mass fraction. You can see that there is a hyperlink here, and you can click on it, and that means I will bring immediately the units manager for this calculation, and I want to change the inflows units. I want to change those inflows units to mass fraction. So I select mass fraction, and this will be the unit, and then click OK. So my brine will be a very simple brine. It will be NaCl, and then 9 mass percent, and then I will have a calcium sulfite, and I will add 1%, and that will give me 100% for my total mass fraction here. And to analyze the results better, I'm going to change the stream amount to 100 moles. Okay. So the next step is to add a calculation. So go to the Add Calculation button and select a single point. And change the single point to a vapor fraction. Okay. And a new grid will appear again. You see the vapor fraction. You need to define the vapor fraction amount. And just let's name this single point calculation as brine evaporation. Okay. So I want to define this vapor amount as 95%. So what this means is that if I put a 95 value there, it means that 95% of the material that I am entering will go to the vapor phase. Okay? So let's click Calculate. And you can see here that in order to make this solution 95% of the total stream go to the vapor phase, it needed 109 degrees C. Okay, and let's go to the report really quickly just to see the phase amounts table, the phase flows amounts table. And in here, since we added 100, or we say, okay, we entered 100 as a total of the stream amount, now I have 95 moles in my vapor phase, and 2 moles in my aqueous phase, and a solid was formed. 2.9 moles of the solid phase was formed. So I'm also interested to know which solids were formed in this evaporation. So what I'm going to go now is to the species output table. And in this species output table, you can see, okay, you added halide. Sorry, you unprecipitating halide, sodium chloride, with 2.75 or 2.76 moles, and I'm also precipitating anhydride, 0.14 moles. So you can always come here to identify how much of a specific phase has formed for this evaporation case. Okay? Questions about this vapor fraction? This is very useful when, for example, we are doing evaporation in lithium ponds, and we want to know what we are precipitating. That's very useful. And if you don't want to form a specific scale on your pipe or something, you just want to avoid specific evaporation rate. So this is a very good calculation for that. So I see that it's 10:53. And we have 2 more single point calculations to go, and then we will start doing the survey calculations. So let's take a break of 7 minutes and then be back at 11, and we will continue with these 2 calculations, which I think are very important for the water chemistry industry. So I'll see you at 11. Thank you. Okay, so since we have one more, oh no, it's 11. Okay, so who is here? The question is, who is here? We have
Adentia here.
good.
Tracy's here.
Who else here?
Yes. Yes, here.
Good. Okay.
I'm here too. It's me.
Great. So it seems most of us are back. So I will go rather a little bit quicker for these two examples because I also want to cover survey calculations today so that we can pay more attention to water analysis in next session. So okay. Now I will do two more single points. This is very important for water chemistry. And these are the set pH and calculate alkalinity. Okay. So the next sample is set pH. So the set pH calculation is very useful when we are either analyzing or designing a process. It allows you to create a solution that conforms to a pre-measured pH. Other applications could be designing a system to meet an operational pH or testing the impact of adding an acid or a base to a system. So what we are going to do in this example is that we are going to compute the amount of base titrant required to neutralize 1 molar acetic acid solution. So let's go back to the software, and I'm going to add a new stream. And then I'm going to call it set pH. For this calculation, the AQ framework is good, and I want to add acetic acid in my inflows. So we have acetic acid, and again, it changes to the formula name. I will leave it as it is for this example. Then we are going to add 1 mole of acetic acid. The next step then is to add the single point calculation. So add calculation, single point. And I know that we are going to do a set pH calculation, but let's run first one as an isothermal calculation to find the pH, the current pH of the solution. So at 25 degrees and 1 atmosphere, the pH of the solution is very low. It's around 2.4. Okay. So, okay, now that we know that this is a very low pH we want to neutralize this. We want to take this solution to a pH of 7. So the next step is, okay, we are going to change that type of calculation to set pH. Okay. So once we bring the set pH calculation, there are 4 new rows. It's going to ask you, okay, what is your target pH? This is a fixed variable. So it's a fixed number. So we said, okay, we want 7 for the solution. And it will ask you, do you want to use a single titrant or do you want to use 2 of them? So the software by default will put the acid titrant as chlorhydric acid and the base titrant as sodium hydroxide. Okay. So whenever it asks you, okay, use a single titrant, the default is not, because if you select yes, you need to know specifically if you are going to add a base or you are going to add an acid. So it's better that we leave the default as no. So use both titrants so the software will know which one to pick and set the pH automatically for you. Okay, so set the pH to 7 and it will use HCl and sodium hydroxide as titrants and then click calculate. Okay, so now the pH here is exactly 7. Okay, and if we want to see why the pH now is 7, what we can do is go to the Output tab, okay, and right-click on the gray area, bring the Sections tab, and add the aqueous section or the aqueous category. So in here, you can see that now the acetic acid is very small. That amount of acetic acid is very small, is around 10 to the minus 3 moles. And that most of that acetic acid has been deprotonated and now is forming acetate. This is sodium acetate that is forming. It's forming around 0.2 moles and is also forming this acetate ion. Okay, and it's around 0.88 moles. So this acetic acid that initially was driving our pH to very low values now has been deprotonated, and now our pH is 7. Our pH is 7. Okay. Any questions about this set pH calculation? Okay, let me just go back to the input. Again, this is a very useful calculation whenever you want to sometimes you want to remove a species from the water, and you know that certain pH will precipitate it out, or you want to conform with specific pH to avoid corrosion or some other standards or values that you cannot exceed. So this set pH calculation is very useful for those situations. The last isothermal calculation that I want to talk about today is the alkalinity calculation. And this alkalinity calculation is very important because we will be using it for the water analysis that will be next class. And alkalinity can be defined as the water's ability to neutralize acids. Alkalinity is also a measure of water's buffering capacity, or its ability to resist changes in pH upon addition of acids or bases. So this alkalinity in water sometimes is due primarily to the presence of weak acid salts, and we have bicarbonates in the water, and those represent the major form of alkalinity in natural waters. And it is because we have CO2 in the atmosphere, and the CO2 then partitions into the water. And also we have the weathering, that it causes carbonate minerals and rocks dissolve and release these carbonates into water. So we are going to calculate the alkalinity of a 1 molar sodium bicarbonate solution. And I will show you how to set up this specific single point. So the next step is, let's add a stream. Oh, I didn't bring the presentation here. So what we are going to do is, we are going to add a stream, and we are going to call it alkalinity. Okay. For this calculation, I want the AQ framework. Also, because alkalinity is reported in milligrams per liter, we should change the units to metric batch concentration, and then click OK. Then in our inflows, we're going to have water, and we are going to have sodium bicarbonate as my carbonate sample, my carbonate species in water, and we are going to add 1 mole. Okay. So then the next calculation is add a single point, and then we go to the reconcile alkalinity option. And we are going to change this name to the single point name to alkalinity only. And okay, in this specific example, We are going, or in this specific reconcile alkalinity single point, there are two calculation subtypes. So we have the reconcile alkalinity and pH option that you see here. This is the first type. And we also have the calculate alkalinity option. Okay. So we will start with the simplest calculation, that will be the calculate alkalinity only. So what the software is going to do is that the software will adjust the alkalinity endpoint pH to 4.5, and it will be using sulfuric acid as a titrant. The amount of sulfuric acid needed to both neutralize the bicarbonate and then reach the endpoint of 4.5 pH is then converted into the alkalinity number. Okay, so it seems that now we are ready to perform the calculation, and then we click calculate. So to the right, in the summary box, you can see that the alkalinity number was calculated as 2.66 milligrams of bicarbonate per liter. And additionally, your pH is around 7.7. And you may be wondering why this pH is 7.7 if we set it up at 4.5. This is because the pH of the initial solution was calculated first, and then the alkalinity was calculated. Okay, so this is the simplest way of calculating the alkalinity. Now we can change this calculation to the reconcile alkalinity and pH. Okay, so just click in the type, in the calculation type, and select reconcile alkalinity and pH. And now my grid got even bigger. Now what's happening here is that since I want to reconcile alkalinity and pH, now I have more things that I have to enter in this grid. But what do we mean by reconcile alkalinity and pH? What does that mean? So what reconciliation means within the software is that the software will match your recorded pH and alkalinity values. So if you have a solution and you went to the lab and you measure your pH and your alkalinity, you can enter them into the software, and the software will adjust the pH by using acids or basic titrants like sodium hydroxide or chlorhydric acid. And for the case of the alkalinity, if you also enter the measure alkalinity, what the software is going to do is going to say, okay, I'm going to use CO2 as my titrant, and I will use sulfuric acid as my alkalinity pH titrant in order to reach a 4.5 as the alkalinity endpoint pH. So yes, basically what reconcile means is that the software will match your recorded pH values of your water analysis. So if we go back to the software in here, we say that, let's say that this measured alkalinity for this water that we enter down here is 160 milligrams of bicarbonate per liter, and that my measured pH is 7.8. Okay. Now this, as I mentioned before, these dots in here, it means that you need to fix these values. So that will be the measured alkalinity. The software fixes this endpoint to 4.5, and this will be the measured pH. And this will be acid titrant, base titrant by default, and the alkalinity titrant, CO2. So then we are ready to calculate this reconcile alkalinity single point. Now, to the right, you can see that these results are a little bit cluttered here. So what I'm going to do is I'm going just to go to the Output tab down here, Output tab, And the next step is that I will tell it, oh no, in here it's already is showing. So what the software is saying, okay, in order to match your alkalinity value, it needed to add 2.68 10 to the minus 3 moles of CO2. And in order to match the pH, it needed to add 2.6 10 to the minus 3 sodium hydroxide. Down here, you can also see the values that were entered into the software in order to match that pH and that alkalinity. Now, if you want to see the values of alkalinity and pH, you can right-click on the gray area, go to Sections, and then click on Additional Stream Parameters. Okay? Now, in here, you will see the alkalinity value, which the software met is 160, and the pH, 7.8. Okay? Now, if you don't want to report this alkalinity as bicarbonate per liter, you can also click on this hyperlink unit, and you can change your units to carbonate per liter. Oops, I'm failing to go there. Okay, so milligrams or carbonate per liter. And then click OK, and it will show you the value as carbonate per liter. Okay, any questions about this alkalinity calculation? At the beginning, when I was learning about this, I was a little bit confused. So I just want to make sure that I'm doing a very good job here trying to explain what does reconciliation mean, especially because we will be using this for water analysis and scaling tendencies, which is very important for the water chemistry industry. Any questions about this? It's all clear? Okay. So this ends our demonstration for single point calculations. And then we will start working on the second type of calculations, which are the survey calculations. Okay. And so now for the survey calculations, this can be considered as a series of single point calculations. So within the software, we have three different types of different ways of setting up a survey calculation. The first one is the single survey. In here, you can choose one independent variable to study its effect on a specific property. For example, you want to study the effect of temperature on density. So you can do that with that single survey calculation. Then we have the dual survey calculation. And in here, you can choose the effect of two independent variables. Could be temperature and pressure on the solubility of a gas. And then we have the survey by changing the single point calculation type. By default, the software, as you saw before, you have the isothermal calculation as the default. And you can actually change, you can go and change the different type of calculation to, for example, a precipitation point. And I will explain this type of survey in more detail as we go in the course. So the first example that we are going to do with survey calculations is a simple temperature survey. So what we are going to study here is how a four-phase mixture partitions as a function of temperature. And the composition of this stream will contain primarily water, or will contain primarily one phase component, or one component for each phase. So for example, for the aqueous phase, it will have water. For the gas phase, it will have methane. For the organic phase or second liquid, it will have decane. And for the solid phase, it will have sodium chloride. Okay, so let's go to the software and let's add a new stream. And in this new stream, we are going to call it survey calculations. So in here, we are going to put different types of calculations. For this calculation, let's change it to the MSE framework. And the metric batch moles, the units by default are good. We're good with that. The next step is to go to Add Calculation and select the survey calculation. Okay. So by default, the survey is by temperature. That's the default survey that the software selects. So, and that's the survey that we are going to do for this example. Let's name this survey temperature survey. Temperature survey. Okay. Then in our inflows, let's start adding. So the first component, it will be water, 55 moles. Then we have methane, CH4, and that will add 15 moles. The next component is decane, so I'm going to put it as the name, decane, and it should recognize it. It changes to the formula name. Let's put 15 moles. And then we have sodium chloride, and that would be another 15 moles. That will give me a total stream amount of 100 moles. That is being calculated in this green cell. Okay, now we need to define the range at which we want to study this speciation, not speciation, but the distribution of these phases as a function of temperature. Let's go to the specs button, and then in here it will open the survey options, and you can say, okay, I want that this survey starts from 25 degrees up to 100 degrees. I think this is a very good survey range, but I want to change the increments to 2 degrees C. And notice how immediately it changes to the number of steps to 38. So it will calculate, it will have 38 number of steps plus my initial calculation, so it will be 39 steps. And then we say, okay. And in the summary, you can see, okay, in here, you want to do a survey temperature, this is the range, this is the step size, this is the number of steps. And then you say, okay, I want to calculate this. Calculate. Now, how can we see the results for this survey calculation? Now we don't have one single point, we have so many points. So what the software has is this new tab that you see here, the plot tab. And by default, the software is plotting the phase amounts in grams of liquid 2, solid, and vapor. So this is the liquid 2, this is the mass of liquid 1, this is my solid phase, and this is my vapor phase. Okay? And what can we see here? We can see how each phases or how this system is partitioning as the temperature changes. So we can see that as the temperature is increasing, the mass of liquid 2 and the mass of liquid 1 decreases as this temperature increases because it is evaporating. We are heating this up. And as a result, the vapor phase now increases, as you can see here, as the temperature increases. The solid phase, which is these yellow triangles, this solid phase stays more or less constant, and it starts to increase a little bit here because as we decrease the liquid 1 phase or the aqueous phase, so then it cannot hold more solids in water, so then it starts to precipitate out. So if you want to know the distribution of phases at a specific temperature, let's say this temperature, 57, what you need to do is mouse over the data point, and on the top of the left corner there is this box here, this gray box here that you see. it will indicate the variable and the coordinates at that point. So now I'm mouse hovering over this point here, and you can see that in the top left corner of this plot, it says that this is the mass of the liquid 1 in grams at 59 degrees C, and the mass is 1,296 grams of this liquid 1. Okay, you can also access the tabulated data and analyze the distribution at each temperature, if you prefer. Okay, so this is how we set up a simple survey by temperature. And now we can move to another simple survey that we call, and is the pH survey calculation. But let me just check here. I received a message, a chat, so I have a question here. So the question is from Amanda, and she says that she wants to know the differences between the MSC aqueous and the MSC SRK model. When would you use each one? Okay, so for this is I know that having the option to select between the AQ and the MSC and the MSC SRK is a little bit confusing sometimes. But I would say, Amanda, that for the AQ framework, it's mostly when you know that you have dilute solution. So whenever you have salt, like let's say NaCl in water, and you have a very dilute solution, 0.1 molal, 2 molal, it is good. The AQ will serve the purpose of calculating properties for diluted solutions. Now, when you start adding more and more and more and more salt to that water, then it starts to get concentrated, and then the AQ framework is no longer it's not going to be able to calculate properties for this solution. So that's why the MSC model was created. The MSC, what it does is it stands for mixed solvent electrolyte, and what it does is whenever you have a lot of concentration of cations and anions in solution, it's a thermodynamic model that is able to calculate properties of these super concentrated solutions. So then we are talking about, you can calculate properties of a 40 molal, 50 molal, or very saturated solutions. So that is when the MSC can work very well. The MSC also is, we're trying to, internally at OLI, we're trying to move, or we develop constantly the MSC model. So the MSC model would be like the preferred model to use for your chemistry in general. It would be preferred because in there you will find more species, more components, and also it can work for higher temperatures, or yeah, it can work for a little bit higher pressure temperatures than the AQ. And the MSC SRK, that is specific for upstream oil and gas when you have high temperatures and high pressures, and if you have light hydrocarbons. Okay, so if you have methane, you have CO2, H2S, and you have a high temperature. Let's say you have a temperature of 100, and then you have a pressure of a temperature of 100 degrees C and a pressure of 100 atmospheres. So this model will be better to calculate the properties of solutions at these conditions. I hope that this makes a little bit more of sense for you. But we can always provide more documentation for you so that it's more clear for you how to set up this or when to use the specific model. I know that internally we are also developing like an artificial intelligence within the software so that it can help you to understand, depending upon your chemistry, which model will be best for you.
Hey, Diana, it's Mike. I want to add something there.
Sure.
One other thing that we did, folks, was we have these monthly spotlight sessions, and one of them was on how to select the right framework. So we could, as part of the distribution for the course, we could ask Dira to provide a link to that spotlight session that would let you see how AJ framed that and how it was presented. It gives some background. Obviously, it's difficult to say for every case, but it does give some guidance as to where each one is useful.
Yes, that's very. Yeah, we can send that specific video as well.
Yeah.
Okay. Thank you.
Just to clarify on that question, is the limitation that like how the calculation is made?
Is the different? Is going to be a different thermodynamic model. So yes, is how.
So is there like a maximum like ionic strength or something for the AQ that you can?
Yes, the ionic strength would be higher than 40.
40. Okay. Lower than 40, right?
Oh yeah, lower than 40. If it's higher than 40, so then the MSC is better for your application.
Oh, okay, got it. Thank you.
Yeah. I guess I should have said that instead of going through all of this explanation. But yeah, so the ionic strength will be that value. And to answer Jan's question, SRK stands for Swavy-Redlich Kwon equation. So it's the SRK equation for the second phase or organic phase when we have this is actually for the organic phase and for the gas phase. So what we do is we use the SRK equation of state to calculate properties of the organic and gas phase. So that's what MSC SRK stands for, and is specifically for upstream oil and gas industry. Okay.
To add just a little bit to that too, so the actual calculation difference is in the activity model. So there's a third term in the activity model for MSE that makes it a little more accurate, and it actually uses hydronium ions instead of H+. So H3O+ is the anion in solution rather than H+. So it's a slightly different treatment of how the dissociation of water is handled as well.
Yes. Okay, thank you, Mike, again.
And actually, Diana, I have in my old notes that we used to present, I have up to 30 molal is about what the cap is on AQ.
You have up to 30 molal. Okay, so Amanda is up to 30 molal. Maybe it's up if the ionic strength is. Okay, I thought for concentration is 40 molal.
Okay.
The ionic strength is different for this case.
Gotcha. Yeah.
Okay. So then we have to cover some other survey calculations. So let's keep on going for this course. So we are going. The next survey that we are going to do is the carbonic acid system as a function of pH. We are going to do the pH survey. Okay. So let's go to the software and add a new stream. No, sorry, maybe below the survey calculations. Just add a new stream. And let's name it, a new survey calculation. So under survey calculations, let's add a new survey. And then let's name this survey as pH survey. Let's select the AQ framework for this survey. And I'm good with metric batch moles. I want to understand the carbonic acid system, so I'm going to enter CO2 as my inflow. Then I enter 0.001 or 1 times 10 to the minus 3 moles. For the survey type, now let's change it to pH survey. Okay, and now you see that the target pH here is highlighted in yellow, meaning that we need to provide a range. And that range has been predefined by the software from 0 to 14, and a step size of 1, and total number of steps of 14. And now I need to define, I say, okay, I want to do this acid carbonic system, but I personally believe that this 0 to 14 range is too broad for the carbonate system, because most of this deviation occurs between 4 to 12. So let's go to the specs button, and let's change the survey range to from 4 to 12. So again, once you go to the survey options, it will ask you, okay, which pH titrant do you use? Do you want to use by default HCl, sodium hydroxide? Then we go to the survey range, and I want to change this survey range from 4 to 12. I also want to define finer increments to see a better or a smoother curve. So I will say I want increments every 0.1 pH unit, and this will calculate a total of 80 points. Okay, so let's click OK, and then we are ready to calculate. Now, to see the results, we need to go to the Plot tab, and in here you will see that the default plot is the moles of added chlorhydric acid and sodium hydroxide versus target pH. And you can see that it's very difficult to see this HCl amount here, so let's click or right click on the left y-axis and select logarithmic scale. Okay, now it's easier to see what's going on in this system. So it's telling me that the software added a small amount of chlorhydric acid to reach up to 4.6 pH, and then it started to add sodium hydroxide to reach the target pH. But this is not the target variable that I want to display, so let's change those variables. Let's go back to the linear scale, so right click here and unselect the logarithmic scale, and we want to change the variables. I want to change the variables that I want to show here. So let's click in this variables button in the top right corner of the plot, and this will bring a new window where you can select all of the data that you want to plot. And there are more than 1,000 variables that you can plot in OLI. And what OLI does is that it puts them into categories so that it doesn't look like a lot of information here. So the first category is the string parameters. This string parameters is the one that we enter every time in our definition type. The inflows is, again, the inflows that we enter in our definition tab. The additional string parameters. This additional string parameters is very important because in here is where you will always find the pH value and also the density. In the phase flow properties, you will see also information. You can see the mass, the distribution of mass, or the moles, or the volume, depending upon what you want to see. Other very well used is these pre-scaling tendencies or scaling tendencies. This pre-scaling, this is 1, 2, 3, 4. This would be anything related to scaling tendencies. Okay. The aqueous, vapor, solid, and molecular categories will give you information about composition. So if you want to understand what are the aqueous species, you will find them here. And the MVG totals, these MVG totals, this MVG stands for material balance groups. And in here is basically the software is selecting or categorizing the oxidation states of specific elements in the system. So in here you can see how much of inorganic carbon you have in the aqueous phase. Okay. So you can always explore these. I just presented the ones that users use the most. Down here you will see more information, thermodynamic information, K values, entropy, etc. But I want to plot the carbonic species in the aqueous phase. So I go to the category of the aqueous phase, and I want to select carbonates. Oh, but in here I have, in my Y1 axis, I have sodium hydroxide and chlorhydric acid. So I don't want them. So I can either double click on them to make them go, or select it and then click the left arrow and make it go. To select, you can also double click and it will just go to your Y1 axis. Then I also want the H+, and also use this button to the right. I also want the bicarbonate species, and what else? The CO2 AQ in solution. And then I click OK. So is everybody good here? I just don't want to go quickly here in the aqueous phases. So I have selected the bicarbonate, H+, the carbonate, and the CO2 and the
I don't see the aqueous tab. I only had liquid 1.
Okay, so select liquid. It means that you are in the MSc framework, but it's okay. You can expand the liquid one, and instead of the H+, you will see the H3O+, that stands for the hydrogen ion, and the rest will be very similar.
Okay.
Then we can click calculate, OK, in here. And this will give me the speciation or the carbonic acid system for bicarbonates, like how do they change depending upon the pH. One thing that I wanted to mention here is that the reason why the end point for this plot is useful for that is to explain why the end point of alkalinity pH is 4.5. And the reason is because at 4.5, the bicarbonate species below that pH is no longer stable. The species that is stable is this H+ species. So that's why it ends the end of alkalinity here. So this is very useful to know. Any questions about this speciation and how to select variables to plot? Jan, did you manage to create the plot?
Yes.
That's good. Was it very similar to?
Very similar.
Okay, that's good. Yeah, that it should be very similar because we are not defining a very high concentration of CO2. So they should act very similar. Okay. So that is our pH calculation. Another thing that I want to mention is about exporting and copying your data for future analysis. So you have different options to export this data. You can right-click on it and select copy, and then you can take it to a spreadsheet, I don't know, Excel, and then you just say Control-V or paste option, and then you will see your data in Excel. That's one way. Another way to export your data is like a CSV file, a comma-separated file. You can right-click and say Export CSV, and then you can name it and save it. That's the second way to do it. The other way to do it is you go to the View Data and select this table here in the corner. You select, if you click on it, you will select all the data, and then Control-C in the keyboard, and then if you go to Excel, Control-V. And if you want only the plot, then you can just go back to the plot and say right-click, copy scaled image or save image as. So it will let you know they will create this image, and again you can paste it in a report, and then you have your image for reports. So you'll have all of these options to explore your data. Okay, so this is how we set up a pH survey. And the next survey that we are going to do is the solubility survey. And what I want to study in this case is that I want to calculate the solubility of sodium chloride as a function of temperature. And for this case, what we are going to do is to set up a survey, but then we are going to change the calculation type to the precipitation point. And let me show you what I mean by that. Any questions, Jan?
No.
Okay. So let's add a new stream, or we can do it, let me see. Yeah, let's add a new stream. And let's name this as survey calc type, because this will be when we change the calculation type in this survey. And we are going to use, in this case, the MSE framework and the units, metric, batch, and I want to use, since it's solubility, I should use concentration, milligrams per liter, and then click OK. So the next step is add a survey calculation, and by default it selects the temperature. So we are going to rename the survey as sodium chloride solubility versus temperature. Okay, now let's add sodium chloride in my inflows. So since I want to understand the solubility as a function of temperature, I'm going to instruct the software to calculate that amount. And to do that, we need to go to the temperature specs here. And the software is going to say, okay, which is the range of temperature you want to study? And I think we should start this from 0 to 100, and then 1 degree C increments. That will be my temperature range. Now, the next step is to change the calculation type. And let's click here to the left, calculation type. And this will bring the type of calculation that is selected by default. In this case, is the isothermal calculation. Now, click on it, and you will see the calculation types that we covered previously. You will see here the precipitation point, and click on it. This is to calculate solubility. And so the software will be asking you, okay, what is the solid that you want to precipitate, and what is the adjusted inflow? For the precipitation point, the software needs to set a small amount of solid to form, or the first crystal to form. So for this example, let's select halite, solid. And for the adjusted inflow, let's select sodium chloride. And then click OK. Now, again, this is like if we would have set up a precipitation point calculation. We brought the precipitant and the adjusted inflow. And then we are ready to calculate. So I want to mention two things that I haven't mentioned before, and is that down here you see all of these calculations tabs. These are the single point calculations at a specific temperature. So this is at 15 degrees C, and you will see the results for each single point. Or you can go and expand here in the survey, and you can also select each temperature to see the results at a specific temperature. But it's easier if we are able to see the results in a plot version. So click on the plot in the results for plot or the plot tab, and in here you can see that the software has calculated, or the default plot for these results is the solubility of sodium chloride as a function of temperature. Okay, so it seems that as the temperature increases from 0 to 20 degrees C, the solubility decreases, and then as the temperature starts to increase, then we have that the solubility of sodium chloride increases. You can also add some other variables to the Y2 axis if you want to see some other variable, like, for example, how the pH changes as the temperature and the solubility increases. So you can go to variables and select the add additional stream parameters, expand it, select pH, and then put it in the Y2 axis, and then click OK. And in here you will see how the pH changes as both the solubility and temperature increases. Okay, you can always save this plot. This is one of the plots that you will be plotting over and over again. You can go here to the plot template manager and give it a name. You can say this is solubility and pH. Oh, I already have one. It's called solubility and pH. Let's put solubility and pH 2, and then you save it. Now you want to go to the default plot, you can always go to the default plot, or if you want to see now the pH and solubility, you can select it and you will see that plot. And one last thing is, if you want to get rid of this pH line here, you just can right click on it and say, just right click on a data point and say remove or hide. So let's remove it. And then you go back to your original plot. Okay. So any questions about this? How do we set up a solubility versus temperature calculation in the software? Am I going too fast?
Nope.
Okay, good.
Oh, it's good.
Okay, so it seems that we have 8 more minutes, 7 more minutes. So what I am going to do is I'm going to just try to run a last calculation, and that last calculation will be the boiling point versus the concentration of sodium chloride. And then we will have some other examples for the beginning of next class that I want to show, and then we can start with the water analysis. Okay, so for this example, we need to do a survey, a composition survey, and then we want to use the bubble point calculation type. So let's do it. Let's go back to the software. And, what is my mouse? Let's create, under this survey calculation type, calc type, let's create a new survey. And then let's name it boiling point versus composition. A long name, boiling point versus composition, so that we don't forget what was that calculation about. So then let's select the MSC framework. I want concentrations of metric batch concentration units. We're good. Then we need to select the survey, change it from temperature, and let's change it to composition. So again, what are we trying to do here? So we want to vary the composition of sodium chloride and see the effect of this concentration on the boiling point. Okay, so we are going to vary the composition of NaCl. So let's add NaCl in my inflows. And since I want to vary the NaCl, I don't need to enter a value. In fact, the software is saying the component that you want to vary has not been selected for the composition survey. So what you need to do in this case is go to the specs button, and it will prompt you to this window where it says, okay, what component do you want to vary? And I say NaCl, and I go to the survey range, and I say, okay, I want to vary this concentration from very, very small value, from 1 milligrams per liter to 300,000 milligrams per liter. Okay, and these are a lot of points. These are too many points. I don't want to calculate this many points. So when we are doing the survey calculations, we also have the option to plot in the logarithmic scale. Okay, so let's select this log scale here, and I'm going to instruct the software that I want to calculate only 20 steps. And that means that the software will change the concentration every 15,000 milligrams per liter. That's good. Now, we don't want to study at one temperature. We want to study the specific boiling point. So we go to the calculation type and then select the bubble point calculation. And I want the bubble point temperature. And then click OK. Now we're good to go. Notice that now the NaCl is yellow, meaning that it will range in the concentration that we put. And now the calculate button says, okay, we are going to calculate bubble point temperature. And we are ready to calculate. So then we can go to the plot. And in here is by default is calculating or is showing me the boiling point as a function of sodium chloride. But this data is not, I'm not happy with this plot. It's very difficult to read. It's cluttered in the corner here. So we can do logarithmic scale in the x-axis. So right-click on the x-axis and select logarithmic scale. And now you can see a more easy to read plot. And you can see that as the concentration of sodium chloride increases, the boiling point of this solution also increases. So, for example, at this 300,000 milligrams per liter, the boiling point is 106. Okay, so any questions about this specific calculation? This is how we set up the boiling point as a function of NaCl composition.
My calculation point doesn't turn green after I follow this step.
Okay, so do you see any error? It's telling you, are you seeing an error or saying that you need to select something?
It's red, so if I do that, it says component not select for composition.
So what you need to do is, next to the composition button here, go to the specs. And select NaCl.
Okay, I thought. Oh, okay. I didn't click it. Okay. I have to click. All right.
Select it, and then go to the survey range, and you will be able to put the range that you want to study.
Yeah. Okay.
Okay, so it seems it's 12 now. This is the end of the first session of this course. Next time we will be able to do a little bit more of calculations for the survey type of calculation, and then we will start moving towards the water analysis. So we will stop here, and then we finish the survey calculations next time. So I'll give it back to you, Mike or Pat, if you are here.
Perfect. I'll be happy to take it. So yeah, thanks everybody for your time today. What we'll actually start on Wednesday is with questions. So we encourage you to take today and tomorrow to work on some of the cases that Diana's gone through today. Work on some of your own cases if you like, if you want to try and apply them to your own work. Just kind of play with the software, see what you can do, see if you have things that don't make sense, if there are questions, and then bring those back on Wednesday morning, and we'll start with those first thing before we get back into the scripted part of the course. But we encourage you to definitely spend the time and bring those questions. We can help you understand anything that's not clear from today or that you may have come across in the interim. So that's really all from me. Everybody, again, thanks for your time, and we'll look forward to Monday. Or Wednesday, excuse me.
Wednesday.
Yeah, Wednesday.
See you Wednesday. Thank you so much.
Excellent. Thank you.
No problem.